Okay, we are talking today about power management in an electronic system. And as usual, we take as a reference electronic systems, a smartphone. So the issue of power delivery and power management in a smartphone is complex because there are different subsystems that require different supply voltages, and therefore you start from one single battery, typically in a modern system a lithium-ion battery that has, for example, when it is full charged, voltage of 3.7 volts, 3.8 volts. And then, starting from that voltage, you need to obtain all the different types of supply voltages that are needed for the different types of subsystems. Also with sometimes different requirements. For example, of course, you need to provide power supply to the CPU. And in modern CPU, the power supplies can vary. We already discussed this issue. For example, in the example of this diagram that I'm showing you, the supply voltage for the CPU varies from 0.8 to something like 1.2 volts. You remember the issue, depending on the load of the CPU, on the computational load of the CPU, we need a higher clock frequency or a lower clock frequency. And in order to have a higher clock frequency, we need smaller propagation delays and therefore a higher supply voltage, if you remember the equations that we obtained together. Which means that for the higher clock, high load means high clock frequency, and therefore we need to supply we need to provide a supply voltage of 1.2 volt in this particular example. If the computational load is smaller, because the CPUs has to do a smaller number of tasks or smaller tasks, then you can reduce the clock frequency, and if you want to reduce the clock frequency, you can also reduce the supply voltage. And in this way, the only reason to further reduce the supply voltage is in order to save in terms of power consumption, because if you remember, at a given clock frequency, the dynamic power consumption is proportional to the supply voltage to the power of 2. So, for example, by reducing the supply voltage from 1.2 to 0.8, one is able to reduce by half the power consumption at the parity of everything else. So, at a parity of clock frequency, at the parity of, let's say, computational performance of the CPU. And this is done dynamically. Talking with the operating system basically negotiates with the power management system what is the proper supply voltage for the CPU. And this is one issue. Then the other point is the other important subsystem that needs to be provided with power is the dynamic RAM banks. DRAM, of course, need supply voltage that is usually constant and different from that required from the CPU. If you basically because there's no need to adjust the supply voltage. In the DRAM, the main power consumption occurs when you want to dynamically refresh all the cells in the memory. Therefore, typically one can simplify things and use only one supply voltage, but with a particular requirement that this supply voltage needs to be very stable, very well fixed. So this is the reason why, if you look at this situation, we have in the diagram of the power delivery network a DC-DC buck converter for the CPU core, which is a converter that, starting from a higher voltage, provides a lower DC voltage, in this case from 3.7 to something close to 1 volt, for example, for the CPU. But then, for example, for the DRAM, you need to do the same thing, but you also need an additional block which is called LDO, which means low dropout circuit, and is a linear regulator. Which has the property of being able to provide a more constant and better regulated voltage. So, which is required in order to supply power for the DRAM, because if you have a voltage that changes, this change can inadvertently let's say, switch some memory content. It can provide a disturber that can switch some memory content, maybe with a low probability, but in a large DRAM, it always, some errors like that always happen. So when you need a very constant and regulated voltage, you need to provide an additional block, which is typically called an LDO. For those of you that have follow the basic electronics course in the bachelor, in the laurea triennale, you have called it linear regulator. Okay, as you probably know, this LDOs, the linear regulator, provides a very nicely constant voltage, but with a relatively small power efficiency. And this is why you typically need a previous DC-DC buck converter, which is a switch converter that has a higher power efficiency, and then you use the LDO just to regulate the final, to do the final tuning of the voltage. Okay. What other possible subsystems do we have? We have, for example, the audio codec for input-output, which means basically the control of the loudspeaker and of the microphone. And they are analog circuits that typically require a higher voltage. So you see another quantity, which means that you need a different buck converter and a different LDO. And again, analog systems require a very constant supply voltage, so you need again an LDO. And then you have other subsystems, the camera, the photo camera of the phone that typically requires a higher voltage again, and the display backlight, which consists of LEDs, and they need more than 3 volts in order to be switched on. So you have this quite different range of voltages, and you need to supply them starting from the same battery. So what happens? You can see the thing. Typically, the power delivery network is not that simple. You have different converters and different LDOs, and also a very well distributed network over the OR board in order to provide the power supply to all the blocks. In more recent years, this power delivery network has been integrated in a single chip. So the typical situation we have now in smartphones, but also in tablets, in PCs, especially let's say the smallest one, you have one single relatively large chip that takes care of all the issues related to power delivery. So in the same chip, we have all the converters and all the LDOs, and basically you have as an input to the chip the battery voltage, and then many different outputs all going to different supply, to supply a different sub-system. This is a relatively important piece in the smartphone. There are several companies that are dedicated to designing and fabricating power management chips for this type of systems, for mobile systems in general. There are a few of them. I already mentioned, some of them are also based in Italy. I already mentioned sometime Dialog Semiconductor, which has exactly this type of business. They develop the power management chips for smartphones and other electronic systems. They are in Livorno. Then there is, for example, a company that is called Silicon Mitus in Pavia, which is doing the same thing for the Android world. Dialog basically does it for the Apple world, and I mean there's a good presence in Italy of this type of companies. So what we are going to do now is to look with some detail at the operation of these converters. You see that sometimes you need to go from 3.7, to something like 3.7 to 1 or close to 1 volt, and this is called a step-down converter, because you go from a higher voltage to a lower voltage, and the step-down converter is also, I mean, traditionally called a buck converter. But sometimes you also need to do the opposite thing, because if you can see here, the backlight of the display needs a higher voltage than the one provided by the battery. And then you need the step-up converter, so a converter which receives as an input a lower voltage and provides an output DC voltage that is higher than the input one, and that is called a boost converter. So at least we have to look into the details of these two types of architectures. There's actually more than that in a smartphone actually, or in a mobile system, because for example, if you have, let me add this because this can be useful, if you have some flash memory or an SSD or an SD card, then in order to program and erase this type of memory, you need something like 10 volts, which of course is obtained from another type of boost converter. But let's say the only thing is that in this case, typically, the converter is integrated in the flash memory chip. So you don't see it in the power management IC, you see it already in the chip of the memory, and then you provide a power supply to the memory that is relatively small. It can be directly from the battery, or can be something like 1.2 volt or 1.5 volts. So, but you have some additional converters. There is maybe another thing to add that I actually already mentioned when we did this teardown of the iPhone. Also, the radio needs to have a separate power supply. The radio is extremely sensitive to disturb and noise, and they typically need a very, let's say, low disturb and separated power management circuit for all the radios, which means for the cellular radio, for the Wi-Fi, for the Bluetooth. They are all independently supplied with another specialized power management IC, which is anyway connected to the same battery. Okay, now let's start by considering this DC-DC converters, and they are used in many additional systems in addition to the smartphones, which is our example. Of course, they're used for portable electronics. They are typically used as DC power supplies. Also, for example, for a battery charger or for an energy bank, power bank. You need to have on board a DC power supply. And another very typical use of them is as a motor drive, because typically the way to drive electrical motors is to modify the supply, to adjust the supply voltage provided to them. So by adjusting the supply voltage, you modify the torque or the velocity or also the angle of an electrical motor, and therefore they're widely used to drive electrical motors. The typical block in which they are introduced is the typical system in which they are introduced is shown here. Basically, this is the load, which is the system that needs to be provided with power, and the DC converter provides this regulated power supply to the load. Let's say going upward, what we have is that we can obtain as an input from the DC-DC converter a battery, as in the example that I've shown before. And in the case of a battery, you typically have a filter capacitor in parallel to the battery, and then so that, let's say, you have as an output of the filter to the filter, let's say this is the battery. Then you have this filter capacitor, which simply is used in order to, let's say, provide current impulses that the battery typically cannot provide. And then you have the DC-DC converter, and then the load. So this is what we call an unregulated DC voltage, and it is not regulated because, of course, there's nothing that regulates it. The DC voltage you have here is the DC voltage that you have on the battery, which is, let's say, at a maximum value around 3.8 when the battery is full, and then decreases as long as the battery is discharged. So it's really not regulated. There's no way to fix this voltage. You need to fix the output one, and this is what the DC-DC regulator is for. The other option is that instead of having a battery, you have a line voltage here, and this is, for example, the typical situation I have here now with my computer, or the situation that you have when you use a battery charger of the smartphone. In that case, I mean, the system is the same. The only difference is that you need to have from the plug here, where you have the 220 volt AC, to the filter capacitor, you need to have a rectifier, which basically transforms the voltage from an AC one to a DC one. This is a simple diode rectifier of the type that you have seen in the basic electronic class. Of course, also here you have a voltage that is DC, but is also affected by some ripple and is not regulated because it really depends. It is proportional to the amplitude of the line voltage from which you start. Okay, now we are focusing on this part, and we want to, let's say, achieve some quantitative understanding of DC-DC converters in the various modes of operation. We're going to see the first two types of converter, but it's useful to mention all of them. I already mentioned the first two types, the so-called step-down converter from a high voltage as an input to a lower voltage as an output. It's also called buck. And the step-up converter is also called boost. This is also an interesting and sometimes useful type of converter, the so-called buck boost, that has the property of providing an output voltage that is of the opposite sign with respect to the input voltage. So it can, so basically this changes the sign. In absolute value, the output voltage can be either higher or lower than the input one, but the important thing is that it's reversed. The sign is reversed. And then the Chook converter is in principle similar to the buck boost, is used in the same situation in which you need to use the buck boost because it also changed the sign. And the full bridge converter instead is mainly used for motor control. Okay, but anyway, these are not so interesting from our point of view in this course. We are focusing on these two main types of converters. Those of you that have done the basic electronic course here have already seen the basics of these two types of converter. We are going to go a bit deeper in this class. Okay. Now, let's focus on the main on the basics of the operation of a step-down converter. So we want to reduce the voltage. The main way to, the most intuitive possibility to reduce the voltage is to use so-called PWM switching. PWM stands for pulse width modulation. So we modulate the width of pulses using a train of pulses, so a sequence, a periodic sequence of pulses. And what is the rationale? Basically, when if this is the input on the left and the output on the right, let's assume that you want the input in a step-down converter is going to be higher than the output. The one thing that you can do is to, let's say, drive this switch, and when the switch is on, the output voltage is equal to the input voltage. So VO, V out, is equal to VD. And when the switch is off, the output voltage, of course, it is zero, because this resistance does not receive any current from a generator. So if you periodically turn on and off the switch, you can obtain as an output a rectangular waveform which goes from VDD to zero. And so the average value, the average of the value of the voltage is something in between VDD and zero. So this is the situation. When the switch is on, VO is equal to VDD. When the switch is off, VO is equal to zero. And then you can go periodically, and depending on the width of this pulse, the duration of the time during which the switch is on, that in this graph is called T on, then you can modify the average value of VO. Okay? Of course, you don't have at the output a constant voltage. You have a voltage that is varying with a frequency that is equal to the switching frequency. But it has a constant component that depends on T on. So let's focus for the moment on the constant component. And the constant component is, of course, if Ts is the switching time, the period of the switching time, Then you can compute the average voltage by integrating VO over a period and dividing by the length of the period. But of course, if you integrate VO over the period, you have VD times T on, and then you divide for the length of the period, that is Ts. So this is the formula that you have at the end. The average, I use the capital letters to indicate the average quantities. The average value of the output voltage is proportional to the width of the pulse, to T on. This is the main principle of operation. Of course, you can say, okay, but I have a lot of other components. I would like to have a constant voltage, but of course you can filter out easily the components at higher frequencies, and then at the end it's relatively easy to obtain only the DC voltage component. So, what I want to stress one thing. Why this is interesting? The reason why this is interesting is that you see, in principle, a switch does not dissipate any power. Ideally, a switch does not dissipate any power. And the reason is that when the switch is off, the current is zero, so the power is the product of the voltage on the switch times the current through the switch, and then the power is zero in the case of a switch that is off. When the switch is on, so in this case I is zero, and therefore P, that is V times I, is equal to zero. When the switch is on, then the voltage drop on the switch is zero, because ideally the switch has zero resistance, so when it's on, it does not dissipate any power, and therefore the current can be even high, but the product of the voltage times the current is again zero. So ideally, if it's true that either the voltage or the current is always zero, and this is the ideal behavior of a switch, it's not the true behavior of a switch, but ideally the switch is not going to dissipate any power, then in this system there's nothing that can dissipate power. Of course, you need to put a filter in order to eliminate the components, the AC component of the output voltage, but you can make a filter with inductors and capacitors only, and inductors and capacitors do not dissipate any power. So, in practice, there's nothing that is dissipating power, and you can have a very high energy efficiency. In principle, you can translate all the power from the input at a non-regulated voltage and move it to the output at the voltage that you want, and that you can adjust with by adjusting the T-on without dissipating any power in the middle. So this is the reason why this type of converters based on switches have become so popular. Okay? Of course, this is an approximation, because in reality also switches dissipate a little bit of power, but of course they still have a very good energy efficiency, and it is the reason why they are widely employed now. Now every power supply is a power supply based on switches that are typically called a switching converter. This is a switch converter, and also your battery charger is typically a converter based on switches. Now, it's important that we examine these assumptions. We need to consider what we actually need to do in addition to this very simple circuit to the DC-DC converter in order to make it work. So what are the assumptions that are really a little bit too ideal and really cannot work in practice? The first problem is that typically the load is not an ideal resistance. It has an inductive component. This is very typical. What's the problem if the load has an inductive component? For example, has a small inductor in series. The problem is that the inductor is inertial with respect to current. So if you try to rapidly change the current in an inductor from a finite value to 0, the inductor resists this behavior and modifies the voltage at its ends in order to counteract this behavior. And this is exactly what happens here. For example, if you start with the switch that is on, and then you have current through the load, then at some point you turn the switch off, the current in principle would go to 0, and what would happen is that this voltage would go down to very low levels in order to, we can say, to suck current from the switch. And this changes in the node voltage can actually create damage on the switch. So this simple thing cannot work. You need to always consider that if you want to rapidly change the voltage at the ends of a load that has an inductive component, you typically end up with having very high voltage or low voltages on the nodes of the inductor that can provide damages, can damage the circuit. So this has to be taken into account, and it requires some modification. And of course, I already mentioned this point, the output voltage must be continuous, which means that we need to, we have said we need to filter out the high frequency components, the components that are not DC, but we need to exactly say how we're going to make these filters. And let's say, luckily, is a relatively easy thing to do, because we just need to change the converter in this way. You see, the principle is more or less the same. This is the input voltage that is not regulated. This is the load, and this is the switch. The same components that we used before, but what we need to add is here a low-pass filter before the load, and the role of this low-pass filter is to filter out all the components of the voltage that are not DC. And you need to also add this diode, and the role of this diode is to eliminate the possibility that the current in the inductor changes too abruptly. Okay? Let's us look at the thing into the details. Of course, this is a low-pass filter, is a second order low-pass filter. It's relatively easy to compute, because what you need to do in order to compute the transfer function of this low-pass filter is just to compute a voltage partition due to the presence of the capacitor and of the inductor. I can do the expression here. This is the impedance of the capacitor, and then you need to divide it by the sum of the impedance of the capacitor and the impedance of the inductor. So this is the transfer function of this very simple circuit. If you multiply by Cs, the numerator and the denominator, we have something like this. And this is a second order filter. You see, basically have two imaginary poles at a frequency that are, so the poles are plus or minus j 1 over square root of LC. So omega p is 1 over the square root of LC. So with this information, if you make a Bode diagram, you end up with something like this. You have a low pass behavior, so zero poles, so zero zeros and two poles. You have a low pass behavior. Before, if this is omega and this is the amplitude in dB, okay, what you have is that up to here the transfer function is constant, that in correspondence of omega p you have two poles acting, so this is going down with minus 40 dB per decade. Okay, so it's a simple second order low pass behavior, and of course if this pole is smaller than the switching frequency, you're going to eliminate all the components at the switching frequency and at the higher order harmonics of the switching frequency. If you consider the rectangular wave that I've shown you before that you would have at the output, the rectangular wave would have, let's say, a DC component. So this is a log scale. So DC component would be at minus infinity. Then you would have a first component at the clock frequency and the switching frequency, a second component probably at twice the clock frequency, the switching frequency, sorry, and so on. And then you can cut them off if omega p is much smaller than omega s, which is exactly the expression that I've written here. So you have to choose properly the value of the inductor and the value of the capacitor in order to eliminate all the components of the signal except for the DC one, which is the one that you really want. Okay? The important thing to understand here is that this filter is made of reactive elements, an inductor and a capacitor, which do not dissipate energy. So you're not going to lose power in this operation. Okay? But by the way, let me stress this point because it is relatively important. Why it's important not to dissipate power in the converter? I'm assuming this is obvious, but probably it's interesting to let's say discuss a bit about it. Why it's important not to dissipate power in the converter? Okay. There are two reasons for that. Of course, I don't want to dissipate power because it does not make any sense. It is not used for doing something in the electronic system. But there are two important reasons. One, which is the most obvious one, it's not the most important one, but I mention it first. One is because, for example, if I have a battery-operated device, I want to preserve the duration of the battery. If I do not dissipate power in the converter, but I only dissipate power in the load, in total I'm dissipating less power, and therefore if I have a battery-operated device, the battery is going to last longer. And this is for sure an important thing, but it's not so. I mean, it's important. Let's say, let's admit it. It's important. It's important for portable devices. It's less important for devices that are in any way connected to the line voltage, such as this one. But the most important thing is that the power that is dissipated increases the temperature of the converter. Because, of course, the power that is dissipated is transformed in heat, and therefore it's increasing the temperature. And that, of course, is a problem. It is a problem for a portable device because it becomes hot, and you need to find ways to eliminate this heat. So you need to have a good heat sink, and you typically need to make the device larger in order to dissipate heat more easily. And also in the case of supply, a DC supply such as this one, the point is that if it becomes hot, then I need to find a way to dissipate the heat, because at something like 150 degrees, this stops working. So it cannot become too hot. And in order to make it not too hot, I need to dissipate the heat faster. And typically, in order to dissipate the heat, I need to make it larger. Because if it's larger, it has a larger surface, and it's easier to dissipate the heat. And if you look at what happened in the last few years, the main reason why these supply voltages, these DC supplies became smaller and smaller, it's simply because they became more and more efficient, and so they could become smaller and smaller. Okay, so the energy efficiency is important from the point of view of dissipating heat, and therefore the final volume of the system, and from the point of view of course, having a longer battery duration. Okay. Now, let's go on. We have discussed about the filter, and we need to discuss a bit about the diode. I mentioned the use of this diode. What is happening with this diode? Okay, let's look again at what happens when we turn the switch off. When the switch is on, the current is going this way. Okay? We have a current through the inductor, which is, in this case, IL. It's a certain current. Now, of course, in this situation, the diode is in reverse bias, because you see the voltage applied to the diode is exactly VD when the switch is on. And if VD is positive and the diode is this way, it means that the voltage, it's a reverse voltage is applied to the diode. So the diode is off. Okay, so in this situation, we have the switch that is on and the diode is off, which means that no current is passing through the diode. Okay. When the switch is turned off, such as in this situation, what happens is that no more current is coming from the input to the inductor, but the inductor needs to have current. I mean, it does not have a will. Is that simply the way it works when you have a reduction of the current in the inductor, the voltage at the ends of the inductor change. And in which way they change? They change the way in order to counteract the decrease of current. And so this node goes down in order to call for more current. And in the absence of the diode, we said that there was a problem because this voltage could go very low and therefore apply a significant stress on the switch. But if the diode is present, when the voltage goes down to minus V gamma, which is the voltage at which the diode is turned on, then the voltage can stop here because the current in the inductor can finally come from the diode. So the presence of the diodes basically ensures that the voltage on this node does not go at smaller voltage than minus V gamma. So here, actually, to be precise, here the current goes at something that is minus V gamma, which is the voltage with the diodes. The diode conducts, the diode is turned on, but for all our purposes we can approximate this V gamma with 0 because it's a smaller voltage than VD, and we can, let's say, make this simple approximation. So in the end what we have is that when the diode is off, when the switch is off, the diode goes on and provides the current to the inductor and ensures that we do not have a stressing change of the voltage on this node. Okay, so and this is the basic operation of the step-down converter. Of course, in order to adjust the value of the voltage, of the constant voltage on the load, as we have seen, we only need to adjust the T-on. By modifying the T-on, that is modified typically digitally with a controller, with a digital controller that commands the switch, we can adjust the output voltage basically as we want. We can, for example, compensate a variation of VD. VD, the input voltage, can be the voltage on a battery. If the battery goes down and we want to have the same voltage at the output, we just need to increase the T-on in order to compensate for a decrease of the battery, of the voltage on the battery, and so on. So this is the easy way to do it. Okay, now this is the principle of operation, let's say, expressed in qualitative terms. Let's now look into the details from a more quantitative point of view. So we need to make some calculations, and for example, we can consider what is happening at the inductor. And probably we need to use this part that is in which we have the whole circuit. So let's consider the situation. This is the voltage on this node, on the node at the input, okay, VOE. You see, it's the same one. So it goes from VD, when the switch is on, to, we have said 0. In principle, it's a bit less than 0, but let's say it's 0 for the purposes of this reasoning, when the switch is off. Okay? The output voltage is basically the same signal, but after filtering. So it's only the DC part, which is this V0 here. So it's a constant part. This means that the voltage on the inductor is the difference between the two. Is VOE minus VO. So it's positive in this part, and it's equal to VD minus VO, and it is negative in this part. Okay? So the voltage on the inductor changes from positive to negative, and the current on the inductor can have some different situations. Let us now look into details. This is the voltage on the inductor. This is the voltage on the inductor. So, as I just said, during T on is VD minus VO, and during T off is equal to minus VO. Okay? Now, you need to remember the basic operation of an inductor. The basic operation of an inductor is that the voltage on the inductor is equal to L times the derivative of the current in the inductor. So this means that when the voltage is positive, the current is increasing. When the voltage is negative, the current is decreasing. And this is exactly what's happening here. During T on, the derivative of the current in the inductor with respect to time is equal to Vd minus Vo, which is the voltage applied to the inductor, over L. And so it is positive, since of course Vo it's smaller than Vd. Vd is the maximum value that the voltage can reach. So during the whole T on, this difference is constant, so the derivative of the current is constant, which means that the current is increasing linearly. This is IL, the current in the inductor. So during T on, the current in the inductor is increasing linearly. During T off, we have a negative voltage applied to the inductor, which means that the current in the inductor is decreasing. The derivative is minus Vo over L, and therefore we can draw here this expression. Now, we have already discussed this part. This is relatively qualitative. The only quantitative thing that we have added is the fact that we now know the derivative in the first phase during T on and the derivative in the second phase during T off. Okay? We have only added this part. Then we can add another consideration, which is the fact that in a periodic situation, in a steady state situation, this behavior is completely periodic, which means that everything here must be repeated after exactly one period. And for example, also the current here must be equal to the current here. And this gives us an additional piece of information in order to evaluate in detail the relationship between Vd and Vo. So what we can do, make this exercise. We can start from here, increase the current up to here because we know the derivative and we know the time, the duration of this derivative. Then we can decrease the current in this other period because we know the new slope of the current and we know the new T off. And then we can compute this and then enforce that this current must be equal to this one. Okay? So this is relatively easy to do. Vd minus Vo over L is the slope during T on, times T on is this increase, and then we can add the reduction in the following period T off. Minus Vo over L is the slope, times T off is this other piece, and this total variation must be equal, total variation must be equal to 0, because at the end the current must be equal to what we have at the beginning. Okay? And so, with this expression, we can, of course, eliminate L and L in both cases. T on and T off are different, but we know that the sum is fixed, because the sum is Ts, the switching time. And for example, okay, this is just one passage, but what I'm doing is the following. I can make the passage, the intermediate passage is here. Basically, you can eliminate L, that is not important. If you put the pieces with Vd, it's only by T on, is equal to Vo times T on plus T off. And T on plus T off is equal to the switching time, Ts. So when I have this, I can write this expression, which says basically that the ratio of the output voltage to the input voltage is equal to the ratio of T on to the switching period, which in turn is equal to what we call typically the duty cycle. This is a definition, let's say. duty cycle, which is a quantity that by definition goes from 0 to 1. Okay? So by the way, this is exactly the same expression that we had at the beginning for the rectangular wave. Because of course, essentially nothing has changed. The only thing that has changed is the fact that we have filtered out the AC components. But apart from that, nothing really different has occurred. Okay. Again, we have this interesting possibility that we can keep the switching time fixed, and then by adjusting T on, we can adjust VO if there is a change of VD, or if you want different VOs, as for example when you are providing a power supply for a CPU, which needs a different power supply depending on the let's say computational load. So I mean, the operation of the DC-DC converter is in this case is relatively simple. Okay. I did not mention the fact that I wrote continuous conduction mode on top of everything. And why? What does it mean exactly? It means something that is not obvious actually, because you see in this very simple explanation, we have that the current in the inductor is always positive. See, the current here, then is here. You can also see, if you consider the operation, that the average current in the inductor, because the current in the inductor is going in the capacitor and in the load, but on average, in the capacitor, the average current is 0 in a stationary state, because otherwise the voltage on the capacitor would change, and therefore the average current of the inductor is all going to the load. So the average of IL here, this dashed line, this horizontal dashed line here, is also IO, which is the current, IL and is equal to IO, which is the output current, that is the current in the load. Okay? So the average is positive and needs to be positive because the output voltage is positive, the load is a resistor, and therefore, I mean, the current must be also positive. But the important thing is that here in this situation, the current in L is always positive. And that is not so common because it really depends on the average current that is going to the load. Because if we reduce the average current in the load, what can happen is that this point can go negative. Imagine if we reduce the average current going to the load, which can happen because the load can change the power requirements. You can switch off a loudspeaker, for example, and then require a lot less power. Then this point can go down, and that it can go below 0, and that is something that needs to be taken into account, because otherwise it's going to degrade the operation of the circuit. Let's see exactly what is happening. So for the moment, you can just imagine that the average output current is going down because the load is requiring less and less current. So at the limit of this reasoning, what we can have is that this point, which is the lowest value of the current in the inductor, becomes 0, goes down to 0, touches the horizontal axis. Okay? This condition is the limit of continuous conduction. It's exactly the condition that I've shown here. You see, the plot is exactly the one as before. The only difference is that now the minimum of the current is exactly 0. Okay? Now, let's for a moment consider what happens at the limit, just in order to know what is the limit. And then we need to understand what happens when we go below the limit. Okay? And you need to understand that this is a situation that is very, very common, because I mean, you need, you know, in typical situation, when you in typical situations when you have the you have especially when you have a mobile system, you always want to save battery time, and therefore, as soon as you can, you put the device in standby. Okay? And when you, for example, switch the display off and you put the device in standby, the current that is needed goes down by orders of magnitude, by 3 orders of magnitude, something by 2, 3, depending on the situation, orders of magnitude. So you're really changing a lot the average current required by the load, and therefore it's very easy to go, let's say, below this limit. Okay, so for the moment, let's focus on the limit, and let's compute what is the limit. So it's relatively easy, because the point is that I need to know what is the maximum, what is the minimum, the boundary current, so the current that we have at the boundary between continuous and discontinuous conduction. It's relatively easy to understand. It's half the peak-to-peak value of the current. Okay? When the average is equal to half the peak of the current, the peak-to-peak value of the current, it means that the minimum value of the current is exactly 0. Okay? And this is something that we have already computed, that because we already had this excursion. So ILB, which is IL at the boundary between continuous and discontinuous conduction, is equal to half the peak. And we already had the current at the peak, because we could compute it during T on. Is T on times the derivative of the current during T on, which is Vd minus Vo over L. So this is I peak divided by 2. And of course, we can express it in terms of the duty cycle, because we already had done those calculations before. We can write T on as D times Ts, which is basically a definition of D. And then here we know that Vo is equal to D times Vd, so we can put out Vd and write here Y minus D. So this Vd times Y minus D is equal to Vd minus Vo. Okay, that is a relatively simple calculation. And the thing is that you have something, you see the boundary value of the current depends on the duty cycle. And it's interesting to plot this dependence, because of course if you plot ILB as a function of D, which is what we have done here, you obtain a behavior that is parabolic, because you have D times 1 minus D, and it's a so this is just a way to collect all the other pieces and express them as a function of the maximum that the curve reaches. But apart from that, even if you do not consider all the other pieces, D times 1 minus D is a parabola, let's say a downward parabola, that is equal to 0 when D is equal to 0, or when D is equal to 1. So it is something like that. The maximum, of course, is the parabola is symmetric, is when D is equal to 1/2, and when D is equal to 1/2 corresponds to this value. That is easy to compute just by examining the expression. So the boundary between continuous and discontinuous conduction depends on D, which means that it depends on the output voltage, and we know what is the type of dependence. So for current above this, we are in continuous conduction. On this line, we are at a boundary between continuous and discontinuous conduction, which means that the minimum of the current through the inductor is exactly 0. Below this value, we are in a region in which something is going to happen, because what is the problem? For what we have discussed up to now, if I just look at this picture, what I can say is that, okay, when the average current goes down, the minimum of the current goes below 0. Okay? In principle, nothing is changing in the operation of the circuit, but if I look at the initial circuit that I have considered, I see a problem. And why is that? Let me go back a little bit. Look at here. During T off, the current in the inductor is passing through the diode. And of course, the current through the diode cannot be negative. If the current in the inductor goes down and even tries to become negative, then the diode goes off and does not provide any current. So the current, instead of going negative, goes to 0. Okay? So what's happening is something slightly different. Okay, so let's go to this point. Something slightly different, which is this one, this illustration. This is the current in inductor. Okay, so during T on, this is T on. Okay, during T on, okay, we know what's happening. During T off, the current tries to go down. We have a negative variation with a slope that we have already computed and that we already know. Now here, the current would try to go negative, according to what we have seen, but in practice it's not happening because the diode is switching off. And therefore the current goes to 0 because the switch is off and also the diode is off. And then the current remains 0 until the switch is turned on again after one period, and therefore the current can come from the switch. So instead of having two different, let's say, phases in one period, we have 3 different phases. We have a phase during which the switch is on and the diode switch is on and the diode is off. Then we have another period during which the switch is the switch is off and the diode is on. And then there's a third period during which the switch is off, but also the diode is off. So T off is this period, when it is 1 minus d over Ts, and we actually need to split it into 2 different periods. A first period that we call delta 1 Ts, and the second period that we call delta 2 Ts. And of course, d Ts plus delta 1 Ts plus delta 2 Ts are equal to Ts. Okay. This situation is called discontinuous conduction mode, because of course there's a period of time during which there's no current in the inductor. So not during this, you see the inductor is basically separated from either ground or the supply voltage. Okay, now what is interesting to see is what is happening in this situation, how things change, and if most importantly, if this if the operation that we have discussed of the DC-DC converter still works in this type of conditions. Okay? This is, let's say, a phase of operation which is more and more important now, because actually, as I mentioned before, systems always go in standby mode in order to dissipate less power. So the current in the load can change rapidly by orders of magnitude and many times during one single day. So this type of operating mode is becoming more and more important. I mean, 20 years ago it was not this way, because it's very rare. It was very rare to have strong variations of the load. If I had a power supply of a TV set, when I switch the TV set on, basically the absorbed current is constant, and then I switch it off and it's finished. But now we have a very dynamic control of power consumption in all systems, and therefore this part is becoming important. So let's look at the same thing from a more quantitative point of view. Of course, what I need to know is the peak current, but that part is easy. I can compute it because I know both the slope during the first phase, during T-on, and also I know the slope during delta 1 Ts. So I can write the peak current as VDD minus VO over L, which is the slope during T-on, times T-on, which is dTs. Or I can write it as the slope during delta 1 Ts, that is VO over L times delta 1 Ts. Actually, the slope is minus VO over L, but I want to have a positive number here, so I change the sign here. Okay, so the two things are if I, let's say, compare the two things, the nice thing is that I can obtain delta 1 as a function of the other quantities, or also VO as a function of both D and delta 1. So I will need an additional piece of information in order to, let's say, obtain only the dependence of the output voltage on D. But that is going to be more complicated. So the first passage is easy. You see, what I do here is I simply eliminate L, and then I collect the pieces with VD and the pieces with VO. I can eliminate also TS, and therefore what I have is that VO over D, VD is equal to D over D plus delta 1. You see, this is changed with respect to what we had in continuous conduction. In continuous conduction, what we had obtained is VO over VD is equal to D. Okay? In this case, VO over VD is equal to D over D plus delta 1. And we do not know delta 1. We do not know what is the value of delta 1. Delta 1, as you can, let's say, intuitively understand, is going to depend on the output current, but we have not extracted the dependence yet. Okay, let's try to add an additional piece of information. What we do here is the following. We simply take this expression and we substitute VO here in here. We take VO here as VD times D over D plus delta 1, and we put it here. And then we obtain this expression. You see, basically, delta 1 is at the numerator, and the advantage of writing it this way is that we have now a relationship of the current with the input voltage, not with the output, only with the input voltage. And this is going to give us some information about how delta 1 depends on the current. Okay, so this is a simple adjustment. What I'm doing is just calling this part Vd over Ts over 8L as ILB max. The way I put an 8 here is going to be more clear in the following. It's in order to have an easy expression at the end, but for the moment it's just the name of the whole thing. But the point is still I want to have to extract the delta 1 value and to use it in the following. And so now what we do is the following thing. So this is I peak. I need to connect I peak with the output current. So how do I do that? The easy way to do it is the following. This is I peak. The output current is the average of the current in the inductor. So how do we compute the average current? We have to compute the area. We make the integral of the current in the inductor over a single period and then divide by the length of the period. So this is a triangle. The area is equal to the height times the base divided by 2. So this is the height, I peak. The base is delta Ts plus delta 1 Ts, which is this one, and this is divided by 2. So this expression is the area of the triangle. And then, of course, I can if I want to compute the average current, IO times Ts must be equal to the area of the triangle. And so this is the expression. And this is going to give me the relationship between the average output current and the peak current in the inductor. Okay? So I'm proceeding, let's say, step by step. I first have expressed the current peak as a function of the duration of different phases, MVD. Then I can express the average current as a function of a peak. And as you can imagine what I can do now, I simply can substitute I peak from here to here. And many things can be simplified. Because if you look, if I do this substitution, d plus delta 1 and d plus delta 1 go away. 8 is divided by 2 and becomes 4. And you have 4 ILB max times d times delta 1. Okay? Can you actually follow all the pieces? And now I can simply write this expression. I take this part, you see I have here d times delta 1 that I can write as a function of the output current. And then here I have only delta 1, but the easy part is that I can multiply everything by d. And then you see here, I can go from here to here. I have delta d to the second power at the numerator. And at the denominator, I have 2 to the second power plus, instead of d times delta 1, I can put IO over 4 LB max. Okay, that's it. So, what's the meaning of this expression? The passages are quite simple to follow, but the important thing is to understand the main concept. In continuous conduction, I had an easy relationship between the output voltage and the input voltage, because the ratio VO over VD was equal to D. So, and was independent of the output current. Okay, it was only independent of the output current, the ratio of VO to VD was equal to D. When we go in discontinuous conduction, is also intuitive as a thing, because when I change the average current, I'm changing the duration of delta 1 of the period during which the diode is on, and therefore I can think that the ratio of the output voltage to the input voltage is going to depend also on the output current. And this is exactly what happens. This is the new dependence. In discontinuous conduction, the ratio of the output voltage to the input voltage depends both on the duty cycle and on I/O, which is the output current, which depends on the operating condition of the system. Okay, ILB max is a constant. ILB max is a constant, is equal to ILB max is equal to VD TS over 8L. So, yeah, if we are doing this evaluation at constant VD, if we consider constant VD, this quantity is a constant, and therefore this expression gives me how I need to change as a function of I/O the duty cycle in order to obtain the output voltage that I want. Okay. From the practical point of view, what does this mean? This means that a control of the power supply is much more complicated. You need to control the power supply by, in some way, knowing exactly what is the average current absorbed by the load. And the other issue is that when the output current, so the current absorbed by the load, changes, and it can change also very rapidly, you need to change very fast the duty cycle, because otherwise you have a huge change in the output voltage. This is very critical from the point of view of the system, because if you think in terms of the power supply of a transmitter. Okay? A transmitter typically transmits in packets, and it transmits a packet in let's say, low power radios, such as low power Bluetooth, for example. You switch on the transmitter, you transmit a packet, and then you switch off the transmitter. So in the time of a few milliseconds, the power absorbed by the receiver goes up when you transmit, and then goes rapidly down. But still, since the transmitter typically has integrated on the same chip also a receiver, you have the same power supply for both the transmitter and the receiver. When the current absorbed by the transmitter changes so rapidly, if the system is not extremely fast in changing the duty cycle in order to keep the supply voltage constant, you have a huge change in the supply voltage of the receiver, and therefore a significant disturb in the receivers, and therefore typically very poor performance of the radio part. So in practice, this outlet become extremely critical when there's a dynamic management of the power consumption on board. Okay, so let's put the two things together. At least for this part, this is, let's say, a summarizing plot. We can consider the things at constant VD in order to simplify things. And let me show you how we can summarize all the things that we have seen in this plot. So I can plot here the conversion ratio. This is also called conversion ratio, which is the ratio of the output voltage to the input voltage as a function of the current I/O. This is the current normalized on ILB, but it's just the current. Okay, this is just a way of plotting it. So, this parabola is the curve that we have found before, the separation between continuous and discontinuous conduction. You remember, we plotted in that case the current as a function of the duty cycle, and it was a parabola. Now I'm plotting it in the other direction. So when we have a current that is higher than the boundary, we are in continuous conduction. So in this region, we are in continuous conduction. This part. In continuous conduction, VO over VD is equal to VO over VD is equal to D, to the duty cycle. This is what we had found. So what does it mean? It's independent of the current. Okay? So the lines are horizontal lines because they do not depend on the current. If you use D as a parameter, they are exactly equal to the value of the parameter, which means that if D is equal to 1, VO over VD is equal to 1. If D is equal to 0.5, VO over VD is equal to 0.5. So we have a family of curves that are all horizontal and are all equal on the y-axis to the parameter D. And of course, they are independent of the current. Okay. So on this axis, for this particular case, we could also have D, because V over VD is equal to D. So this is the boundary between continuous and discontinuous conduction. If we cross the boundary, we are in a region of discontinuous conduction. Okay? So in the region of discontinuous conduction, so we are here, the expression that links VO over VD to the current is this one, the one that we have just calculated. And of course, we can use D as a parameter, but a few, let's say, some aspects of the behavior are quite, let's say, easy to understand. If I/O is equal to 0, this ratio is equal to 1. So when I/O goes to 0, all the curves go to 1, as we have shown here. And as a function of I/O, they have a, when we increase I/O, this ratio goes down. So the slope is always negative. Okay? The other piece of information that we know is that, of course, at the boundary between continuous and discontinuous conduction, the two curves corresponding to the same value of the duty cycle have to touch each other. Okay? So we need to pass from here. So we have this type of behavior, sort of hyperbole, that is touching the horizontal line corresponding to the same duty cycle at the boundary between continuous and discontinuous conduction, and on the other hand, when I/O is equal to 0, has to reach 1. Okay. So this is basically summarizing what happens in continuous and discontinuous conduction. Just to understand the point, if we, for example, have a single system, that is the example of a receiver that I was doing before, that is switching between a high value of the current and a low value of the current. For example, we need the same VO and we have the same battery. So let's assume that VO over DD must be constant, okay? But the current required by the load changes very rapidly. So in one position, when the transmitter is transmitting, is sending a packet, is this one, for example. And then when the transmission phase is finished, the current absorption is reduced to a minimum and it goes here. Okay, from here to here. So, and the controller has to be extremely fast because here the duty cycle is 0.7 Okay. When I go here, the duty cycle is, I don't know, something probably which is 0.2. So the controller has to sense rapidly the variation of the current and change rapidly the duty cycle. And that is typically done with an embedded processor that controls the switch, that senses the current and adjusts the duty cycle as a consequence. Okay? So this is why in practice these power management ICs have this DC-DC component, which is the one that one typically considers in let's say, investigating the operation of these power electronic circuits. But on the other hand, it has to have a very rapid embedded processor that senses the current and rapidly adjusts the duty cycle controlling the switch. Okay. Okay, this is a good point to stop. We're stopping here now and then continuing next time.